Okay, let's go and get started with what we're going to cover today. And now we're into the part of the class where we're going to be doing kind of special topics that can help you with your game and simulation. So in this case, what we want to talk about is kind of simulating gravitation. In other words, one of the key physical forces that exists in the universe. If we want to simulate that or make a simulation that uses that, that's what we're going to talk about doing today. All right, so to get started here is that the whole idea of simulating gravitation is sometimes we want to simulate something that's realistic in some way. And there can be a number of ways that we want to do that, but most physics simulations that you think about involve applying some sort of force. So for example, when I let go of this, it falls out of my hand. It does that for a reason. The reason is that there's a force pulling this down, and you can kind of feel the weight of that when you hold it. And that force in this case is gravitational energy. Now, what is that energy? How can we simulate it? That's what we're going to talk about today. All right, first off, if we look at the Wikipedia definition of gravitational energy, it says, as a potential energy, a physical object with mass has in relation to another massive object due to gravity. So in this case, the potential energy here that we have is kind of the force caused by the mass of this bottle with the liquid in it being attracted to the mass of the Earth. And that potential energy that's created, it's potential right now, it becomes kinetic when I let go of it and drop it. That kind of gravitational force there that's pulling those two objects together is associated with the gravitational field of each of those objects. And one of the things that, like, why does this fall at the rate that it does? It has to do with the masses of the two bodies and how far apart they are, and what's called the gravitational constant. In other words, what constant is universal, applied across the entire universe with masses, and what force pulls them together. So, for example, obviously the sun has mass. And so the question might be, well, the sun has more mass than the Earth. When I let go of the bottle, why doesn't it fly towards the sun? And that's two reasons. One is it kind of is, because the whole Earth is falling towards the sun as it orbits. But then the second part of that is the Earth is much closer. Even though the mass is lower, the distance is much smaller. So let's look at a kind of a diagram of what we're talking about here to get an idea for what we're talking about. All right, so here we've got our two masses, M1 and M2. There's this force kind of trying to pull them together, and there's a distance apart that they are. And thanks to Newton, we have this nice formula here that says the force is equal to the gravitational constant times M1 times M2 divided by the distance squared. So in this case, you'll notice that M1 is the mass of 1, M2 is the mass of 2. So in our case of the example we just did, M1 could be the Earth, which is a really large mass. And then M2 could be something much smaller. And then the distance between them would be the distance of this bottle from the center of the Earth, the center of that mass. Notice it's not the edge, it's the center of it. And then we would take that, perform that calculation, multiply it times the gravitational constant, and that would give us the amount of force, or what we would call on Earth kind of the weight of this thing, which is the kind of force pulling it down. And you might notice that heavier things, like things that are more massive, like let's say a giant square of a cubic yard of concrete, is going to have a much higher force than something light like a piece of paper. And the reason for that is because the resulting calculation, when you multiply the masses together, will be much smaller with smaller, less massive objects and larger ones. The other thing we'll notice, which doesn't really come into play much on the surface of the Earth, but actually the force of this is going to be higher as it gets closer to the ground. It's going to be lower as it goes up. But that's not going to be so noticeable on the surface of the Earth, but in a larger kind of astronomical context, that will matter. Now, G is the gravitational constant, which is kind of everything gets applied to this entire formula here. But that whole thing produces this force. All right, a couple things to note about this is, first off, the force acts on both bodies with the same magnitude. So in other words, as this thing is being pulled towards the Earth, that the Earth is getting pulled up towards this bottle. So both of them are pulled toward each other. It just so happens that the momentum with the mass of the Earth being so tremendous and the little bottle being much lighter, the Earth is not going to move much or have much of a force imposed upon it by that bottle, because the force is going to be really small relative to the mass. But the bottle is going to fall towards the Earth because it has a much smaller mass with the same force acting upon it. And second note here is, if you look at that gravitational constant, you'll notice this is a really small number, the 6.674 times 10 to the negative 11th. That's if we take this decimal point and move it over this way 11 places. So 0.000000000667 is a really small number. And the gravitational forces, even though stuff feels very heavy, the gravitational force is relatively small. That's why if I have these two objects like this, they don't immediately like pull each other and stick together, because their masses are small. Therefore, the force is very small. But the Earth is really large, has a lot of mass, which is why I can feel the weight of this, where I cannot feel the kind of attraction of those two things being pulled together. The second thing to notice is the distance term is squared in the denominator. And what that means is, since this is dividing, that means that as this number grows, as distance grows, and the squared term grows, we would divide it by a larger and larger number, which would make the overall result smaller and smaller. So in other words, this falls off as the kind of square of the distance. So in other words, the closer two things are together, the more there's a gravitational pull. The farther apart they are, it kind of starts to diminish more and more. It does so kind of in this squared term in the denominator. So things that are far apart will have very little force. Things that are very, very close together will have a lot more force. All right. Now, if we have multiple objects instead of two, so notice back here we have said two objects. If I have more objects than two, and this one should be M3 and not M1, but you'll notice that these three objects all are going to pull on each other. Now, with multiple objects, with all those forces added, we can figure out what the kind of net force is by taking all of these and just adding them all together. So in other words, if I look at that arrow pulling this way at that amount, this arrow pulling that amount, the net result will be kind of pull it down towards the middle. So if I were to just release all of these objects, they'd all get pulled towards the center of kind of all of them, not because there's some magical spot here that has gravitation, but because this vector of force plus that one, if you think about it being like, what's the average of those force vectors, it's going to be somewhere in the middle here. We could also have, if we had a line of three objects, like mass 1, mass 2, mass 3, and the forces were balanced out, the one in the middle might not move at all because they would be balanced. It would be in a balance point. Now, what we're going to do is, I'm going to keep the presentation short and switch over to the code here in just a second. But what we're going to do is we're going to need some kind of an object to keep track of each body. And in the sample code that I have here, I'm going to call that planet. So I made a class to keep track of each planet. And then I just picked a random X and Y coordinate. We have an 800 by 600 screen, so I just picked a random place on the screen. I picked a random color so they're easier to tell apart. I picked a random direction in 0 to 360 degrees. I picked a random mass, which could be really small at 1, or it could be all the way up to, in this case, 30,000. And then down here, I picked this speed that they start off with, kind of a random speed in the direction that they're facing. And this elasticity, the only place I'm going to use that is, I don't have that being used in the code right here, but I'm going to make it so that when the object hits the screen, it bounces off and maybe loses a little bit of energy when it does that. So that way we don't have, otherwise when we run this gravitation sample, if we don't make them bounce off the screen, we're going to end up with objects that kind of completely are flung off the screen and we never see them again. So this is a way to kind of contain it just for our simulation. And we'll see that in the final code when we get to that. All right, now the move, pretty simple. We just take the direction and the speed and compute the offset in y and x. Only thing that's a little confusing on this is this -1, and that's because the coordinate system in Pygame is inverted with 0, 0 at the top left. and y increasing going down rather than the normal Cartesian coordinate increases going up. So what we're going to do there is we just multiply that by -1. And then sine gives us the kind of up and down amount. Cosine gives us the left and right. And notice that we're just computing the dx and dy based on the direction and the speed. Now, when we move the object, we're just updating the position by that. And notice I don't have in this code the kind of bouncing off of the borders yet with the elasticity. We'll see that in the final code. But this is kind of the basic thing if we had a more unlimited universe, how far apart they'd be. And then to render these, all I really did to render these is I kind of took the mass, I took the cube of the mass to simulate kind of the radius of a sphere of that size. And then that's the radius I'm making it. I just draw a circle at that size. And there are two circles being drawn here. This one is kind of to make it look like this little specular reflection on it. I just did like a white circle on top of the circle and offset it a little bit. Don't worry too much about that second circle. It's really just for effect. So we're drawing a circle of a size that's the radius is proportionate to what a sphere would have associated with it. All right, now in order to keep track of more than one planet, we're just going to make a list of them. And you'll notice in this thing, I just make this planets thing that's just an empty list, and then I just add 2 planets to it. If I want to, I could change this and make it 200 or 1,000 or however many I want to make in there, but I'm going to create those planets. Now, once we have the planets, to apply gravitation to all of them, essentially what we want is to apply gravitation like this to all of them with, in this first case, the code's only going to have 2, so it's going to look like that. But what we eventually want to do is have any number of them possible. And in order to do that, we need to go through our formula for every 2 pairs. In other words, we have mass 1 and mass 2. We need to compute the force and then apply it to each of those, mass 1 to mass 2, mass 2 to mass 1, apply it to each of those. And one of the things we can do is we can simplify things when we have more than 2 by just accumulating all the forces and then applying the net force results. In other words, back to this diagram here, what we're going to do is we're going to say compute that force, compute this force, and we're going to accumulate all of them. In other words, the change in the force x and force y, this makes a little triangle, has an x component, or x component has a y component. This one has an x component and a y component. If we just add all of those up, add up all of the x components, add up all of the y components, then that's going to give us this kind of net force, which is the new vector. We're just going to add that. Now, to do that, here's a little bit of code that here we are going through every planet. Here I am getting those kind of 2 components, the sum x and sum y of the forces. I'm starting them off at 0, and now I'm just going to accumulate them here. So for every planet, I'm going to go through every other planet. And what I'm going to do is I have this if statement if P is not Q. And the reason for that is we don't want to have the planet exert a force on itself. So if it is not itself, then we're going to look at it. So in other words, for planet P, if we have another planet Q that's not the same, then we're going to calculate the force. So to calculate the force, first thing we do is the distance. And that's just the distance between P and Q. So the planet of interest that we're on that we're applying a force to, and Q, some other planet that's not the one that we're on. And notice what I did is I add this thing. If they get too close together, I go ahead and combine the masses of them and make a new one. And what this is doing here is this is averaging the direction of them. So they emerge with an average direction, and it's actually a weighted average based on the mass. So a large object absorbing a smaller one will not change much, but if they're 2 about the same, they'll come up with a perfect average of the 2. So in other words, this is going to allow planets to collide and become one planet after they collide. Not a super accurate simulation, but it makes it so that we can have planets kind of coalesce or group together into larger masses over time. And I didn't really use the radiuses here that I computed before. Maybe I should have. But of each of them, based on the masses, like I did when I drew the thing, in this case, I just had this hard-coded 4 there. So 4 pixels away, they become 1 mass. Now, in the else of this, if they're not close together, rather than combining them, I just compute the force. So notice here is Q mass times P mass. That whole thing divided by radius squared. There's my gravitational formula there, times the gravitational constant, which I can set that to different values and see what happens. But if I wanted a really hyper accurate simulation, I could set that to the actual gravitational constant in the universe. I could pick like the mass of this bottle. I could pick the mass of the Earth. I could set the distance from the center of the Earth to this bottle, and we would get out of that force, we would get the actual amount of force that is actually exerting on my hand when I'm holding that thing up. So we could make this hyper realistic if we wanted to. Now, after I do that, I compute the kind of dx and dy, and notice that this is kind of I'm using this to compute the, this is kind of a vector subtraction of q and p to find out the direction between those two things. So this is the force direction. I just use arctangent 2 and put dy, negative dy because that inversion of the coordinate system, and dx, and then convert that to degrees. So this is giving me the direction of the force that's acting between P and Q. The next thing I do is I take that and I convert it into the component and multiply it by F. So this gives me how much of that is in kind of the X, how much is in Y. I multiply that by the force that I calculated here to say, so I have this amount of force, it's just a magnitude. I need to know how much of that is affecting X and how much is affecting kind of the Y of that. So we divided it into those X and Y components, and I just add that to sum. And as I go through all the planets, we add the next one, add the next one, add the next one. So the end result after I'm done with this for loop, going through all the planets, is going to be the overall net force that's acting on planet P. So the last thing I do here is I take that amount and I essentially compute from that, let me go back. I essentially compute from that the, apply that force to the existing thing. So here's the existing speed and direction. I essentially apply that here. I divide it by the mass to account for momentum of the object. I add that to the dy and dx, and then that becomes the new speed and the new direction. So notice I had a speed and direction up here. I now have a new speed and direction after I apply the force to that mass, the net force to the mass of the planet that I'm on. So after I'm done with that, I've now applied that amount of force. And so let's actually take a look at the code in action. So I'm going to just switch over to the code here quickly. All right, so here's the actual full code. And let me just kind of quickly look through this. Again, here's the planet. Here's the same movement stuff we already saw. The only difference here is I added this section of code here. And what this section of code here is doing is just bouncing off of the border. So in other words, if my y is less than 0, I change the dy and then invert the dy. And notice I multiply by the elasticity to remove a little bit of the energy when it hits the wall. So it's not a perfect collision. It loses that. In this case, it's 70% of the speed that it was before. And I just do that for all of the edges. And then the rest of this is the same. Here I am making my planet list. I set my gravitational constant to something fairly large in this case, much larger than the real gravitational constant. And that's so I could see these things move without them moving at very slow terms. And again, just like if I had small masses and a small realistic gravitational constant, I would put the two things on the screen and they would be hardly affected at all. So I'm kind of magnifying that by making the gravitational constant much larger than it really is. The next thing I do is I have my event loop, and the main part of the event loop that really matters is down here where I'm going through all the planets, checking each one against every other planet. If it's a different planet, apply the force, calculate the force, accumulate it. Once I've accumulated all the forces, apply them just like we had on the previous slide. And really that's it. So what we're really doing here, clearing the screen, going through every planet, moving it, rendering it, going back, accumulating forces, applying the force, move a planet, render a planet, and so forth every time. Now, if I were to kind of refactor this code, I'd probably put the apply force thing into a thing. I'd probably make a planet list class that applies all the forces to all of them and make it much cleaner in the main. But since what we're after here is really kind of looking at this code here. We'll just keep it kind of, I wouldn't say clean, but simple without as much abstraction, so you can see all that happening there rather than hiding that in the objects. If I were writing this code for a real game, I'd probably hide that into the objects. But let's actually see this in action. All right, so I'm going to go and run it. Okay, so here it is. Notice there are two objects on the screen. And notice one of them has a smaller mass than the other one. You notice they're not being affected too much, but when they get closer together, so right now it looks like they're not really affecting each other much at all, but that's because they're far apart. Now as they get closer together though, you'll see kind of that slingshot effect that has. And sometimes that will get a really high speed that causes them to affect each other. So here as they get closer, you'll see the smaller one especially being curved more than the larger one. That's because of that momentum where we're dividing the force by the mass. And there's another kind of slingshot. And now we have the blue one kind of orbiting and then flung way out away from that. And notice that, that this works with more objects too. So let's try it. Here's 3 objects instead of 2. You notice that they're all going to be affecting each other. So they're kind of, now we have the orange, those two got too close together. And if you've ever watched like Star Trek or anything like that, there's like this always this use. Let's use a star as a slingshot to gain speed and acceleration. And that's what they're doing. Is they're getting, if you get close enough to a star, you get this kind of immense amount of force that can end up flinging you away from it. And actually, NASA does that with spacecraft, where they use planets to assist in their kind of navigation instead of having to burn a lot of fuel to do that. And you can see that happen here, where something's moving slowly. It'll get near one of the other more massive objects, and it'll slingshot away from that, like those two just did right there. And those are roughly close to the same size. All right, let's try it with more objects. Here's with 4. And you notice they're all affecting each other. So this is kind of an n-body thing. Here's a bunch of them. You notice the smaller one being flung around more than the larger ones. So that little tiny green one really getting thrown around by the other objects. Here's a whole mess of them. And these ones, we'll start to see them combining as they get close together. You'll see a number of them decrease. And this is kind of hard to keep track of them because some of them are now being flung around really quickly. But you'll notice that green one is getting larger and larger as this thing progresses. And one of the ideas I had when I wrote this simulation was, what happens if I made like a really large object, like a sun, like a solar mass, and I put some smaller objects more in the range of like planet-sized objects in around that. But I used the same kind of simulation that I have here. And so let's look at one other example of this in action. And then what we'll do is we'll come back to that. So kind of going back to this, there's one other one that I made. And that's kind of this central star mass or solar mass with these much smaller objects around it. And what I did is, when I started this simulation, there's actually a cool thing you can do where you can kind of simulate kind of planet formation. Is if the planets still collide with each other, they get bigger. If the star itself collides with the planet, it consumes them. But what I did is I started kind of like a cloud of these planet masses that were relatively small. I allowed them to join together, but I also made it so that when I first created them, they had a slight swirl to them. And what you'll see is you end up with this kind of solar system that gets created from this. Some things will behave like comets, where they're moving much more elliptical orbits. Some things are much more circular. Let's take a look at that code in action as well. So let me go back to my Python here. Let me end this one. Oh, you'll notice that simulation was running while we were looking at the slide, and now we're down to just 4 objects, where one of them is very massive now. All right, let's go ahead and stop that. Let's go to our other simulation. So here's the planetary orbit simulation program. And notice the code here is pretty much the same. There's a planet. There's movement. The only real difference in here is the direction that I picked here is set up to be around the center slightly. So rather than just having a totally random direction where they all just go everywhere, this is actually giving them a little bit of a swirl around the center. Everything else in here is pretty much just the same. Let's go and run it and see what happens. So you'll notice that we have that center mass. You'll notice if you look really close, you can see that wobble a little bit. And as a lot of planets get on one side, the star will wobble a little bit. And I'm also keeping this centered. I also made this so you can kind of zoom in or zoom out. So you'll notice that there are some of these planets way out here that are kind of just escaping. And you'll notice here's the solar system here, and you'll notice that sometimes one of the ones toward the middle, if it gets too close, will get flung out like that one did. And there's one that's eventually probably going to stop and then come back in. Let's zoom back in on that. Let's go about right there. So notice here is one way out here moving slowly that's going to have some kind of an orbit. And here's one that has a nice circular orbit in here, this green one. And notice those eventually can combine with each other, especially where they're crossing orbits. But you'll notice with nothing more than just throwing kind of some objects in here randomly, giving them a little bit of a swirling motion. Oh, there's a thing like a comet that just got flung way out there. But over time, what you'll see is things that have a stable orbit will stay. Things that have a kind of a erratic orbit where they might get flung out and away and we'll never see them again. But you'll notice that this will kind of evolve and change over time, and what we'll be left with are only the things that had stable orbits in our little fake solar system here. And I can actually make just a few. Like there's one, there's two. There's some that are very close that have a relatively stable orbit. And remember, there is randomness associated with this as well. So here's a bunch of them. You'll notice some of them are really getting flung out away from the center. So if we zoom out, you can notice that some of these are just leaving. We'll never see them again. But some of them are going to get pulled in. Some are going to orbit. It's actually a kind of a fun thing to play with. Here's one that's now orbiting in the opposite direction, which they all started with the same swirl, but here's one now that somehow is now orbiting opposite the other ones based on how it interacted with other things. An interesting thing about this, these are actually interacting with each other as well. They're not just interacting with that star. They're interacting with each other. So they can affect each other. They can combine with each other as they're moving around. So again, here's the one moving opposite. Here's the one like a comet. And some of those that are really far out, like this guy here, will eventually come back in. All right, so that can be a fun thing to play with. And notice, again, it's the same math that does that. And that's actually the math that governs our solar system and our universe and galaxies and everything else. It's the same math that we're doing here that we're just simulating. All right, so you may be able to use that in your game. Let's switch back to the presentation for one final kind of little thing here. And kind of to finish up here, a couple notes. That you can extend that to have as many objects as you want. So if you want to simulate all the asteroids in the asteroid belt and all the planets in the solar system and all the kind of satellites of those planets, or you want to simulate the Earth with all of the kind of man-made satellites that do communication and defense things and scientific things, you could do that. All you have to do is know the masses of the objects and then their speed and their distance apart, and we could start a simulation and simulate that over time. And that's the kind of thing that astrophysicists do. Also the kinds of things that aerospace engineers have to do from time to time, space scientists have to do. But really only the limitation is how much memory we have devoted to storing those objects, and then how much processor time we have to do the computations. And notice that we could actually improve the performance of what we're doing right now quite a bit. One of the things we're doing is we're actually computing. We said that if we have two objects, the force between them is the same. We're really computing it twice, once for one object, once for the other one. We could just do it once and then not have to do it again. The second thing to note here is that the force calculations are the same whether we do this in 2 dimensions as we are now in simulated or 3 dimensions. So we could actually extend this simulation really easily to like a 3D kind of gravity simulation where we have a full solar system or Earth with satellites or whatever we want. Also, we could set the gravitational constant to accurately model the real universe rather than my kind of made up 0.1 just to see things going around relatively quickly. But we could set it to other values as well. In fact, you could set it to be negative and simulate anti-gravity, and then you'd have objects that repel each other. That could actually be pretty interesting to play with as well, that you could make some objects that attract, some that repel, and you could make something like a puzzle game out of that you to put the planets in the right position to make some object travel through the universe to get to some destination place. So there's a whole lot of interesting stuff you can do by just changing the gravitational constant or changing the masses of the objects. All right, so that's all for today. I will post the source code to the webpage. If you have the course page, if you have any questions, ask in the comments or send me an email. You should be working on your projects. If you think this gravitation stuff will help with your game project in some way, you should incorporate that. Again, it's super easy to incorporate. All you have to do is know kind of that Newton's formula for gravitation. And then if you have a lot of bodies, just accumulate all the forces to a net force, apply the force, and that's it. So it's relatively simple. The math is relatively straightforward and stuff that we've done before. So don't be afraid of that. And again, you can get something really hyper accurate or hyper realistic with this method because that's the way the universe works. All right, so we'll go and stop there. And I'm not sure what we're going to do next class, probably another special topic. I've got a few more I want to get through this semester, but you should also really be working on your project, and we should have some sort of a project update that I'll post an assignment for soon. All right, stay safe.